Welcome to the course on error control coding and introduction to linear block codes. So far we have studied what are linear block codes, how do we describe linear block codes using generator matrix and Padicek matrix. We talked about how we can use error correcting codes for error detection and error correction, and we discussed the distance properties of linear block codes. Today we will spend some time solving some problems for linear block codes. So today's session will be on problem solving. So the first problem that we will look at is, let C be a linear code with both even and odd weight code words. Prove that the number of even weight code words is equal to number of odd weight code words. So let us denote the set of even code words in C by C sub E and set of odd code words in C by C sub O. Now let us consider an odd weight code word X which is taken from this set CO, and let us add X to each of the code words which are there in this set CO. So if we add an odd weight code word to another odd weight code word, what we will get is a even weight code word. For example, let us say I add 111000 and I add 101010. So this first code word, this is an odd weight code word, its weight is 3. Similarly, this code word also has weight 3. If I add both of them, what do I get? I get 0 1 0 0 1 0, and this is a even weight code word. So when I add X, which is an odd weight code vector, and I add X to each of the elements in this set C0, what I get is a set of even code words vectors, and let us denote that set by CE prime. Now the number of code vectors in CE prime is going to be equal to number of vectors in CO. Why? Because how did we get this CE prime? We added an odd vector X to the set CO. So number of vectors in this set is going to be equal to number of vectors in CO. Hence number of elements in CE prime is going to be same as number of elements in CO. And since we know that this set of even vectors CE hat is a subset of set of even vectors, we can write from this that number of elements in the set of number of odd code words is going to be a subset of number of even code words. Next, let us add the same odd weight code word now to all the vectors in the set CE. So if we add an odd weight code word to set of even weight code words, what we will get is a set of odd code words. So the number of vectors in CO prime is going to be equal to number of vectors in number of even vectors. Why? Because this set was generated by adding an odd vector X to the set of even code words. So, we can then write that CO prime is equal to this. Okay, the set of code words here is same as set of code words here. Now, we know that CO dash is a subset of set of odd code words. So, then from this relation and this relation, we can write that set of even code words is a subset of set of number of elements in this is subset of number of is basically less than number of elements in this set. Now, from this relation and this relation, both of them can be true only if number of elements in C O is same as number of elements in C. So, this relation let us call it 1 and let us call it 2. These two relations are satisfied only if we have set of even code words to be same as set of odd code words. Hence, we prove that in a linear code with both even and odd code words, the number of even weight code words is same as number of odd weight code words. So, I repeat, this condition and this condition will be simultaneously satisfied only when the set of number of even code words is same as set of number of odd code words, and this proves our result. The next problem that we will look at is as follows. Let us consider a linear NK code C whose generator matrix contains no 0 column. Now, arrange all code words of this linear code C as rows of 2 raised power k by n array. So, what we are doing is we are arranging the 2k code words like this in an array. So, this array has dimension 2k cross n, because total number of code words are 2 raised power k for a nk binary code, and they are all n bit. The first result that we are going to show is no columns of this array contains 0. Now, please note that we have been given that this generator matrix G does not contain any 0 column. Okay. So, from the given condition on G, we can see that for any position of any bit position, there is a row in G which has a non-zero component at that particular bit location. And if this is true, what are the rows of, how do we generate the code words? We generate the code words by linear combination of these rows of this generator matrix. And since the generator matrix does not contain any 0 column, so each of these rows can be looked up as code word in C. So, when we generate the code words using this generator matrix in this code array, each column will have at least one non-zero entry. So, this follows from the fact that our generator matrix G does not contain any 0 column, and hence no column in this code array will have zeros. The next result that we are going to show is in this array, in this 2 raised power k cross n array, each column consists of equal numbers of zeros and ones. There are total 2 raised power k minus 1 zeros and 2 raised power k minus 1 ones. So, to prove this, what we will do is we will show that number of code words that have 1 at lth location is same as number of code words that have 0 at lth location, and in this way we will prove that this array has same number of zeros and ones. So, in this code array we know that each column will have at least one non-zero entry that we proved in the earlier result. So, consider the lth column of this code array. Let us denote by S0 the set of code words that have 0 at the lth location, and let us denote by S1 the set of code words that have 1 at the lth location. Now, we pick up a code word x from the set S1, that means x has 1 at lth location. Now, if we add this code word x to all the elements in the set S0, what do we get? What we will get is a set containing 1 at lth location. Why? Because S0 is a set that has 0 at the lth location, and x is taken from the set S1. So, x has 1 at lth location. So, if we add x to S elements in S0, what we will get is there will be a 1 at the lth bit location. So, we denote this class of code word by S1 prime, and this S1 prime will have 1 at the lth location. And since this S1 prime is generated by adding x to this set of vectors in S0, so number of elements in S0 is going to be same as number of elements in S1 prime, and S1 prime is a subset of S1, which is the set of all code words which have 1 at lth location. So, from this we get this condition that set of code words which has 0 at lth location is less than equal to set of code words which has 1 at lth location. Now, add this same vector x which has 1 at lth location to all the elements in S1. When we do that, what we get is a new set of vectors which has 0 at lth location. We denote this set by S0 prime. So, S0 prime is a set of code words which are obtained by adding x to the set of vectors, set of odd vectors which have 1 at lth location. So, then we can write this set of vectors in S0 prime is same as set of vectors in S1, and since S0 prime is a subset of S0, what we can write then is from this relation and this relation we can write set of code words which have 1 at lth location is less than set of code words which has 0 at lth location. Now, equation 1 and 2, they are going to be simultaneously satisfied only when this is satisfied with equality. So, then what it shows here is that at any lth location, number of code words which have 0 at lth location is same as number of code words which have 1 at lth location. So, basically each column will then have same number of zeros and same number of ones. Now, we prove another result. We show that minimum distance of the code is upper bounded by this quantity, and to prove this result we are just going to use the result we just proved in the previous section. So, in the previous section what we did was we arranged these 2k code words in an array, 2k cross n array, and we showed that each column of this array has 2 raised to power k minus 1 ones and 2 raised to power k minus 1 zeros. So, in this whole array which has n columns, total number of ones is given by this n times 2 raised to power k minus 1. Now, since each non-zero code word will have minimum distance at least d min, and how many total code words we have? 2 raised to power k. One of them is all zero code word. So, how many non-zero code words we have? That is given by 2k minus 1, and each of these non-zero code words have minimum distance at least d min. So, total number of non-zero code word multiplied by d min must be less than equal to total number of ones in this code array, which is given by n times 2k minus 1, 2 raised to power k minus 1. So, from this relation then we can then write that minimum distance of a code is upper bounded by this relationship. So, next problem that we will look at is, what is a minimum distance of a linear block code C that can simultaneously correct mu errors and E erasures? Now, just recall what do we mean by error correction and error erasure correction basically. So, erasure is basically some of the bits are getting erased. So, you send n bits, if E bits are getting erased, what you are receiving is n minus E bits. And error correction you are familiar with, basically we want to correct errors that have happened in so many bit locations. So, the question is, what should be the minimum distance of a linear block code that can simultaneously correct mu errors as well as E erasures? Now, if the minimum distance of a code is at least 2 mu plus E plus 1, then it can simultaneously correct mu errors and E erasures. We are going to next prove this result. So, delete from all code words E components which got erased. If we delete these E components, what we are left is n minus E length shortened code word. So, this deletion of E component results in a shortened code of length n minus E. Now, we know that if we want to correct T errors, what should be the minimum distance of the code? It should be at least 2t plus 1. So, this code basically, if we want to correct mu errors, the minimum distance of the code after this E erasures should be greater than equal to 2 mu plus 1. So, if minimum distance of the code after this E erasures, the minimum distance is still larger than 2 mu plus 1, then this code can correct mu errors. So, we want our minimum distance of the code to be at least 2 mu plus E plus 1. Now, since these mu errors are in the unerased positions can be corrected if this condition holds. So, as a result basically we would be able to correct mu errors. Now, remember we have to simultaneously also be able to basically, it would be not only simultaneously correct mu errors, but we have to correct E erasures also. Now, what is the condition on minimum distance such that E erasures can be also corrected? The minimum distance of the code should be at least greater than number of erasures plus 1. So, if the minimum distance of the code is greater than E plus 1, then there is only one code word in the original code that maps to the shortened code. So, as long as minimum distance of the code is greater than e plus 1. There is only one code word in the original code that agrees with the unerased component. So, there is, as long as minimum distance of the code is greater than e plus 1, there is only one code that maps from erased shortened code to the original code. And since in this case the d minimum is already 2 mu plus e plus 1, which is greater than e plus 1, this code would be able to correct e erasures as well. So, if we choose a minimum distance of the code to be greater than equal to 2 mu plus e plus 1, it would be able to correct mu errors as well as e erasures. The next problem that we are going to solve is as follows. Prove that a linear block code is capable of correcting lambda or fewer errors and simultaneously detecting L, where L is greater than lambda or fewer errors, if the minimum distance of the code is at least lambda plus L plus 1. Please pay attention to the word simultaneously. So, we want not only to correct mu errors, along with that we should be able to detect L errors as well. That is what we mean by simultaneous error detection and correction. So, let us prove this result. Now, note lambda is less than L. So, if minimum distance is lambda plus L plus 1, this is basically greater than 2 lambda plus 1. And if the minimum distance is greater than 2 lambda plus 1, it would be able to correct lambda errors. So, from this given condition that d min is at least lambda plus L plus 1, where L is greater than lambda, we know that the minimum distance is greater than 2 lambda plus 1. So, it should be able to correct lambda errors. Now, note we want to, in addition to correcting lambda or fewer errors, we also want to simultaneously detect L errors. Now, if we want to simultaneously detect those L or fewer errors, we have to ensure that those error patterns of weight L or less are not in the same coset as the error patterns that we are trying to correct. Now, since lambda errors can be corrected, we can put all error patterns of lambda or fewer errors as coset leader in our standard array, and they can be correctable. Next, to simultaneously detect L errors, we have to show that none of these error patterns of weight L or less are in the same coset as these error patterns of lambda or less error. So, we need to show that no error pattern x of length L or fewer are in the same coset as error pattern y of lambda or fewer errors. If they are in the same coset, because we are using those coset leaders for error correction, we would not be able to detect those error patterns. So, it is important that those error patterns of weight L or less, if we want to detect them, they should not be in the same coset as the correctable error patterns. So, we are now going to use method of contradiction to show that it is not possible to have these error pattern x of L or fewer errors in the same coset as these error patterns y of lambda or fewer errors which we are trying to correct. So, how does this method of contradiction work? We will first assume that they are in the same coset, and then we will show that this is not possible. Hence, our assumption that they are in the same coset is wrong. So, we start our proof by saying these error pattern x of weight L or less and error pattern y of weight lambda or less, they are in the same coset. Now, if x and y are in the same coset, we know from our standard array that x plus y should be a non-zero code word. If you recall the entries of a standard array, we had in the first column non-zero code word, and then we had other code word v2, v3, and then what we had was error pattern E2, and then we had basically this was E2 plus V2, and like that we had. And if you add any two elements of a coset or a row, what you will notice is sum of them is a valid code word. So, if x and y are in the same coset, x plus y must be a non-zero code word. Now, let us look at what is the weight of x plus y. So, weight of x plus y is less than equal to weight of x plus weight of y, because it is possible that there are some common elements between x and y. That is why the weight of x plus y is less than equal to weight of x plus weight of y. And what is weight of x? X are the error pattern of weight L or less. So, the maximum weight of x is L. Similarly, maximum weight of y is lambda. So, weight of x plus y is then less than equal to lambda plus L. And what is the minimum distance? Minimum distance of code is at least lambda plus L plus 1. So, weight of x plus y is then less than d min. So, what we have shown is the weight of x plus y should have been a code word, is a code word if they are in the same coset. If x and y are in the same coset, x plus y is a valid non-zero code word. But what we have shown here is weight of x plus y is less than d min. So, if x plus y is a valid code word, its minimum weight should be at least d min. So, from here basically what we get is it is not possible to have x plus y in the same coset, because if they were in the same coset, x plus y would have been a valid code word and its weight of x plus y should have been more than d min, but here in this case it is coming out to be less than d min. Hence, our assumption that x and y are in the same coset is wrong. Now, if x and y are not in the same coset, then we can always put those error patterns of y and x in different cosets, and hence we can simultaneously detect and correct errors. So, we can simultaneously correct lambda errors while detecting also L errors. Okay. So, again to recap, basically we proved this result by showing that if we want to simultaneously correct and detect errors, those error patterns should be in the different cosets, and hence we can simultaneously correct and detect those error patterns. The next problem that we are going to solve is as follows. Let Ci be a binary linear code with code parameters given by n k I with generator matrix G I and minimum distance d I. And let us consider a new code C, a new binary code, linear code of length 2n and message bit length k1 plus k2, whose generator matrix is given by this expression. Now, what is the minimum distance of this new code C? So, to find out the minimum distance, so let us consider, let U and V are two binary n tuples, and we form our two n tuples as follows. If you look at this code word V, how is this code word generated? So, it is one n bit code word, another n bit code word. First n bit code word is generated using U times G1, and second one you get basically U times G1 plus V times G2. So, essentially the way you are generating this code word, the first part contains n bit code word U, and the second part is n bit code word which is U plus V. So, this 2n length code word will be of the form like this, where the first n bits are U0, U1, U2, Un minus 1, and the next n bits are of the form U0 plus V0, U1 plus V1, and like that. So, as I said, our linear block code C, the new code of length 2n, can be written as this form, where you have a code U of length n which belongs to C1, and then the second part, which n bit part, is U plus V, where U belongs to C1 and V belongs to C2. Now, we will show that minimum distance of the code is minimum of 2D1 or D2, where D2 is the minimum distance of the code NK2 and D1 is the minimum distance of the code NK1. So, let us consider two distinct code words X and Y. So, X we denote as concatenation of U and U plus V, and this is U prime plus U prime plus V prime. Let X and Y be two distinct code words in C. Now, what is the Hamming distance between X and Y? We can write down the Hamming distance between X and Y as the Hamming weight between U plus U prime plus Hamming weight between U plus V plus U hat plus V hat. So, the Hamming distance between X and Y can be written as Hamming weight of U plus U hat plus Hamming weight of U plus U hat plus V hat. Now, note X and Y are distinct code words. So, let us consider two scenarios. In first case, we will consider V is same as V prime. In second case, we will consider V is not same as V prime. So, if we consider V as same as V prime, since X and Y are distinct code word, what we will have is U is not same as U prime. So, in this case, the Hamming distance between X and Y will be given by Hamming weight of U plus U prime plus, now since V and V prime are same, this will be 0. So, this will be same as Hamming weight of U plus U prime. So, then in this case, when V is same as V prime, we can write the Hamming distance between X and Y as Hamming weight of U plus U prime plus Hamming weight of U plus U prime. And since what is U plus U prime? U and U prime are two code words belonging to C1. So, sum of two code words for a linear block code is another valid code word. So, U plus U prime is going to be another valid code word. So, then what would be the minimum distance of U plus U prime? It would be at least the minimum distance of the code C1, which is D1. So, then Hamming distance between X and Y would be greater than equal to 2 times D1. So, for the case when V is equal to V prime, we have shown that minimum distance should be at least 2 times d1. Now, let us consider the case when V is not equal to V prime. So, before that we will just state again the triangular inequality that we are going to use. So, from the triangular inequality we know that Hamming distance between x and y is greater than or equal to Hamming distance between x and z minus Hamming distance between y and z, and we know the Hamming distance is nothing but Hamming weight of x plus y, Hamming weight of x plus y and Hamming weight of x plus z minus Hamming weight of y plus z. So, we can write this expression in terms of Hamming distance, or we can write in terms of Hamming weight. Now, let us take x plus z to be equal to v plus v prime and y plus z as u plus u prime, and we put these values of x and x plus y and x plus z and y plus z, we put these values in this expression. So, what is x plus y? X plus y would be v plus v prime plus u prime. So, x plus y is basically u plus u prime plus v prime. So, from here weight of x plus y is given by this. Next, what we had was weight of x plus z. What is weight of x plus z? Weight of x plus z is weight of v plus v prime, and similarly weight of y plus z is given by this. Okay. So, this is upper bounded, this is lower bounded by this quantity, this is lower bounded by this quantity. Now, go back and see what is our minimum distance between x and y. Minimum distance between x and y is given by this expression. It is a Hamming weight between u and u prime plus Hamming weight of u plus u prime plus v prime. And what we did just now is we lower bounded this. So, then Hamming distance between x and y can be, so this basically this we lower bounded by this quantity. If we plug that in here, what we get here is greater than equal to. So, what we can write is the Hamming distance between x and y is then greater than or equal to this term comes from here, this term, and this term is lower bounded by this term here. So, we write it here. Now, this can be further written as Hamming weight of v plus v prime, because these two cancel out. So, what we have shown is when v is not same as v prime, the Hamming distance between x and y is greater than or equal to Hamming weight of v plus v prime. And what is v plus v prime? V and v prime are valid code words in linear block code C2 with minimum distance D2. So, v plus v prime will be another valid code word in C2 whose minimum distance is D2. So, then we can write this as Hamming distance between x and y is greater than or equal to D2. So, we look at comparing equation number 4 and equation number 3. If we compare these two equations, we can write that minimum distance of the code is minimum of 2d1 or d2. Okay. Now, let us show that there exists a code with minimum distance of code is indeed equal to minimum of 2d1 or d2. So, let us take two minimum weight code words in C1 and C2, let us call them U0 and V0. Now, this is a valid code word in C, and what is this minimum distance? It is 2 times D1. So, if we take V0 to be all 0 code word, what we get is U0 and U0. This is a valid code word in C, and its minimum distance is 2 times D1. Similarly, if we take U0 to be all 0 code word, then what we get is this code word 0 and U0, whose minimum distance is D2. So, hence we have shown that basically their minimum distance of code of this code, new code C, is indeed minimum of 2D1 or D2. Okay. Thank you.